Welcome to AskPrep, your trusted companion for NEET and JEE preparation. Today we will study about a very important topic of chemistry, which is aromatic compounds, electrophilic substitution and resonance. Aromatic compounds hold a special place in organic chemistry due to their stability and unique reactivity patterns. Among these, benzene and its derivatives are the most studied because of their ability to undergo electrophilic substitution reactions while maintaining their aromatic character. The concept of resonance plays a crucial role in understanding the stability of these compounds and the way they react with electrophiles. Benzene, the simplest aromatic compound, is a six-membered ring with alternating single and double bonds. However, this representation is misleading because benzene does not actually have distinct single and double bonds. Instead, it exhibits resonance, a phenomenon where the actual electronic structure is a hybrid of multiple contributing structures. This delocalization of electrons across the ring results in an equal distribution of electron density, making benzene exceptionally stable. The resonance stabilization of benzene influences its reactivity. Unlike alkenes, which readily undergo addition reactions, benzene prefers electrophilic substitution reactions. This means that instead of breaking its aromatic system, it replaces a hydrogen atom with an electrophile while preserving the delocalized electron cloud. Common electrophilic substitution reactions include halogenation, nitration, sulphonation, alkylation, and acylation. In halogenation, benzene reacts with halogens like chlorine or bromine in the presence of a Lewis acid catalyst such as iron chloride or iron bromide. The catalyst polarizes the halogen molecule, generating a positively charged halogen species that acts as an electrophile. This electrophile attacks the benzene ring, temporarily disrupting its aromaticity. However, the system quickly restores aromaticity by eliminating a proton, resulting in a halogen-substituted benzene compound. Nitration involves introducing a nitro group into the benzene ring using a mixture of concentrated nitric acid and sulfuric acid. The sulfuric acid acts as a catalyst, generating the nitronium ion, a powerful electrophile. This ion attacks benzene, leading to the formation of nitrobenzene after the re-establishment of aromaticity. Nitro compounds are valuable intermediates in the synthesis of dyes, explosives, and pharmaceuticals. Sulphonation is another important electrophilic substitution reaction where benzene reacts with sulfur trioxide or concentrated sulfuric acid to form benzene sulfonic acid. This reaction is reversible and is widely used in the production of detergents and sulfur drugs. Friedel-Crafts alkylation and acylation reactions involve the introduction of alkyl or acyl groups onto the benzene ring using alkyl halides or acyl chlorides, respectively, in the presence of a Lewis acid catalyst such as aluminum chloride. Alkylation adds carbon-containing groups to benzene, making it more reactive toward further substitution, while acylation introduces carbonyl-containing groups, which deactivate the ring and reduce further substitution. The nature of substituents already present on the benzene ring affects the orientation and rate of further electrophilic substitution reactions. Electron-donating groups, such as alkyl or hydroxyl groups, activate the ring, making it more reactive and directing incoming electrophiles to the ortho and para positions. On the other hand, electron-withdrawing groups, such as nitro or carbonyl groups, deactivate the ring and direct substitution to the meta position. Another important reaction is halogenation, where benzene reacts with halogens such as chlorine or bromine in the presence of a Lewis acid catalyst like ferric chloride or aluminum chloride. The result is the substitution of a hydrogen atom with a halogen, forming compounds like chlorobenzene or bromobenzene. These products serve as intermediates in various industrial applications. Friedel-Crafts alkylation and acylation reactions are also key electrophilic substitution processes. In alkylation, benzene reacts with an alkyl halide in the presence of a Lewis acid catalyst, leading to the attachment of an alkyl group to the ring. This reaction is widely used in the production of aromatic hydrocarbons found in fuels and lubricants. Similarly, in acylation, benzene reacts with an acyl chloride, forming aromatic ketones, which are valuable in the synthesis of fragrances and pharmaceuticals. Sulphonation is another significant reaction where benzene reacts with concentrated sulfuric acid, leading to the introduction of a sulfonic acid group. This reaction is crucial in the manufacture of detergents, dyes, and sulfur drugs. The directing effects of substituents play a vital role in determining the position of new electrophilic substitution. Electron-donating groups, such as hydroxyl and alkyl groups, activate the benzene ring and direct incoming electrophiles to the ortho and para positions. Conversely, electron-withdrawing groups, such as nitro and carboxyl groups, deactivate the ring and direct electrophiles to the meta position. This concept is crucial in designing synthetic pathways for aromatic compounds in pharmaceuticals, agrochemicals, and materials science. Resonance in benzene is a key factor influencing these reactions. The delocalized electron cloud provides stability, preventing the ring from undergoing addition reactions. This property differentiates benzene from alkenes, which readily participate in addition reactions. The resonance effect also explains the reactivity differences in substituted benzenes. Activating groups enhance electron density through resonance donation, increasing reactivity, while deactivating groups withdraw electron density, making the ring less reactive toward electrophiles. Understanding the interplay between resonance and electrophilic substitution is essential for predicting reaction outcomes and designing synthetic pathways in organic chemistry. Aromatic compounds and their reactions play a vital role in the development of various industrial and pharmaceutical applications, highlighting their significance in both theoretical and practical chemistry. Their stability and reactivity balance makes them fundamental in the study of organic reaction mechanisms and synthesis strategies. Thank you. We hope this video has helped you gain a clearer understanding of hydrogen and its compounds, especially the fascinating role of heavy water and isotopes. If you found this video helpful, make sure to like, share, and subscribe to AskPrep for more in-depth chemistry lessons. Keep studying, stay curious, and good luck with your exams.